Okay, we're going to do part 2 of our atoms and elements lecture now. So first I just want to briefly talk about the Bohr model of an atom. And the Bohr model says basically we have a nucleus in the center of an atom, and then electrons go around the nucleus like orbits, so like planets around the sun. And as each orbit gets further and further away from the nucleus, it increases in energy. Now, we're not going to talk about this too much because this model has been replaced by the quantum mechanical model. This model isn't very accurate. So like I just said, Bohr orbits were replaced with the quantum mechanical orbitals. Orbitals represent not specific paths that electrons follow, but probability maps that show where an electron is likely to be found. Basically, electrons don't have a predictable path because they exhibit wave-like and particle-like properties, which is called wave-particle duality. And so we have different orbitals with different probabilities, different shapes, and different energies. So let's talk about some different quantum numbers. The first quantum number we're going to talk about is the principal quantum number. The principal quantum number, or n, specifies the principal shell of the orbital. So a higher n means higher orbital energy. So as n increases, the energy increases. The principal quantum number also dictates size. So the higher a principal quantum number for that particular orbital type, the bigger that orbital type is. So principal quantum number, n, relates to energy and size of the orbital. Then we have the angular momentum quantum number, which is L, and this describes the shape of the orbital. It also helps determine energy, and it depends on n. So basically L has multiple different, it can be multiple different things for a particular n. And that's just saying that L is equal to 0, 1, so on and so forth, up to n minus 1. So if I have an n of 1, well, my L can only be 0, because the biggest L can be is n minus 1. And with an n of 1, 1 minus 1 is 0. If I have an n of 2, I can have 0 and 1, because I can go up to n minus 1, so on and so forth. I'll show you a chart a little later on. So also n tells you the number of subshells, and remember L relates to subshells. So for n equals 1, we can have 1 subshell, the S subshell. For n equals 2, we can have 2, S and P. For n equals 3, we can have 3, S, P, and D. And n equals 4, we can have 4, S, P, D, and F. So again, like I said, orbital subshells are a 3D probability map of where an electron can be found. So here's the shape representation of a 1s orbital, where 1 is the principal quantum number. And it's a sphere. If we look at the difference between the 1s and the 2s orbital, all that's changing is the quantum number. And remember I said the quantum number dictates energy, but also dictates size. So they're both spheres, but the 2s orbital is bigger than the 1s orbital. Here's p orbitals. P orbitals are like dumbbells. And there's 3 p orbitals, one in the x plane, one in the y plane, and one in the z plane. Here's the 3D orbitals, and there's just 5 different ones. We're not going to talk about their shape too much. Okay, let's talk about the third quantum number, is the magnetic quantum number, which is m sub L, and this can go between -1 to +1, and this determines orbital orientation. Remember how I said here there's 3 p orbitals and 3 different planes? Well, those planes are determined by its magnetic quantum number. So here's a chart to kind of hopefully help this make a little more sense. So here I have n, or the principal quantum number. Here I have L. Here I have the subshell, and here I have m sub L. So remember, L is dependent on n, and m sub L is dependent on L. So for n, remember L can be up to n minus 1. So for n of 1, we can only have 0. For n of 2, though, we can have 0 or 1. For n of 3, we can have 0, 1, and 2. And n of 4, we can have 0, 1, 2, and 3. So remember, these start at 0 and they go up to n minus 1. And L tells you your subshell. So for an L of 0, that's the S subshell. An L of 1 is a P subshell. An L of 2 is a D subshell, and an L of 3 is an F subshell. And remember, these subshells just tell you the shape of the orbital. So if I have an N of 3, I can have an L of 0, 1, or 2, which means I can have an S, P, or a D subshell. And then M sub L, remember, that is from negative L to positive L. So for L of 0, we can only have 0 because we have negative 0, positive 0. Those are the same thing. Those are just 0. For an L of 1, remember we go from negative L to positive L. So we have L, negative 1, 0, 1. And remember how there were 3 p orbitals? Well, here's your 3 p orbitals. One is negative 1, 1, 0, 1's 1. And that just depends on orientation. For an L of 2, we can have an M sub L, negative 2, negative 1, 0, 1, or 2. This is for the D subshell. If we go back here, see there's 5 D orbitals. And then finally, for an L of 3, we can have an M sub L of negative 3, negative 2, negative 1, 0, 1, 2, and 3. So that means the F subshell has 7 orbitals. And finally, we have the spin quantum number. So the Pauli exclusion principle says that orbitals may hold no more than 2 electrons with opposing signs. So we have spin up or spin down, and just the magnetic spin quantum number can either be positive 1/2 or negative 1/2. That's it. Let's talk about the ground state. The ground state of an electron is its lowest energy state. So for hydrogen, hydrogen has 1 electron at room temperature, and it is in the 1s orbital. This model also allows electrons to transition to higher energy orbitals upon the absorbance of energy. The absorption of energy by an atom can cause an electron to jump from its ground state orbital to a higher energy orbital. And when this happens, we say the atom is in an excited state. Excited states are really unstable, so the electron will usually relax back to a lower energy orbital. And when the electron relaxes, it emits energy, often in the form of light. An energy difference between 2 orbitals determines the wavelength of light emitted. Okay, let's talk about electron configurations. So these illustrate how electrons occupy orbitals. So for example, hydrogen. Hydrogen's electron configuration is 1s1. 1s is the orbital, and the exponent is the number of electrons in the orbital. So it has a principal quantum number n of 1. Its subshell is s, and there's 1 electron in that shell. Then we also have orbital diagrams. So here we have the element. This is in the 1s orbital, and there's 1 electron going up. That's spin up. So here's the energy ordering of orbitals for multi-electron atoms, and that's basically saying here's energy increasing and here are the orbitals. If I go here, that determines the filling order, and I have a diagram in a little bit to talk more about that. But this is just a diagram to see that how the orbitals are dependent on energy. Okay, so let's talk about more electron configurations. So we talked about hydrogen, which has 1 electron. Well, helium has 2. So its electron configuration is 1s2. N is 1, its subshell is s, and there's 2 electrons. And here's its orbital diagram. So we have the 1s shell. We have 2 electrons, one going up, one going down. Then for lithium, now we have 3 electrons. Its electron configuration is 1s2, 2s1. So there's 2 electrons in the 1s orbital, and there's 1 electron in the 2s orbital. And here is its orbital diagram. We have the 1s and 2s electrons. We have 2 in the 1s, 1 in the 2s. And then let's look at carbon. So carbon its electron configuration is 1s2, 2s2, 2p2. So its orbital diagram, here's 1s, here's 2s, here's 2p. We have 2 electrons in the 1s, 2 electrons in the 2s, and 2 electrons in the 2p. Now why don't I just put both electrons here, or one here and one here, or both one up and one down, or both down? Well, that has to do with Hund's rule, which says that when you're filling orbitals of equal energy, electrons fill singly first with parallel spins, both up. So I'm filling the 2p orbitals, and 2p has 3 orbitals, right? And I have 2 electrons. So I put them in the first 2 orbitals within the 2p orbital, and they both go spin up. So here's the filling order. So you can see here, you just follow these. So first we fill 1s, then 2s, 2p, 3s, 3p, 4s, 3d, 4p, so on and so forth, right? You can easily write this out on a test, and I still write this out myself. And how you do that is you just write 1 through 7 on a paper, 2 to 6, 3 to 6, and 4 and 5, just like this. And then in your first column, you put S's, second column P, third D, 4F, fourth column F, and then you just draw arrows through. So I suggest practicing writing this out, but it's really simple to do. And that's the filling order for electrons. So if I have, 10 electrons, I'll start here, here, go here, until I fill all of these. And remember, let me go back here. So since P has 3 orbitals, that means the P subshell can hold 6 electrons, because remember, each orbital can hold 2 electrons. So the P orbitals, if I go back, let me see, sorry. The P orbitals can hold 6 electrons. There's 3 orbitals. You can see it here in M sub L. D has 5 orbitals. That means it can hold 10 electrons. S just has 1, so it can hold 2. So it goes up by 2 every time. So S can hold 2, by 4. S can hold 2, P can hold 6, D can hold 10, F can hold 14. And we're really not going to deal with F orbitals at all. So don't worry about that too much. Let me go back. Okay. So here's just a summary. Electrons occupy orbitals in a way that minimizes the energy of the atom. So we fill lower energy orbitals first. And here's the fill order. But again, it's a lot easier, I think, to see in this kind of diagram. Orbitals can't hold more than 2 electrons each. And that has to do with the Pauli exclusion principle. When 2 electrons occupy the same orbital, they have to have opposing signs. And then Hund's rule again says when orbitals of identical energy are available, they are first occupied singly with parallel spins, not in pairs. So that's why we have here, we occupy each 2p orbital singly first, and then we'll start pairing. So here's some electron configurations for the first, elements 3 through 10. So you can see here, I'm just adding an electron every time. And you can see Hund's rule, let's start here. Okay, we talked about carbon a little bit. It has 2 2p electrons, so we fill each orbital one at a time. The nitrogen has 3 2p electrons, so we fill the first 2p orbital, the second, then the third. Now we've got 4 in oxygen though. So I've already filled all 3, and now I start back at the beginning, but they have opposing signs. Fluorine, we just add another one, and then neon, another one. So again, just to reiterate, the S subshell has only 1 orbital and can only hold 2 electrons. The P subshell has 3 orbitals, so it can hold 6 electrons. The D subshell has 5 orbitals, so it can hold 10 electrons. And the F subshell has 7 orbitals, and it can hold 14 electrons. Okay, so, we get to, some of the elements have tons of electrons, right? We can have elements with 50 electrons. Well, that's a lot to write out, right? Well, we have an abbreviation. It's called the Noble Gas Abbreviation, which says that when you're writing electron configurations for elements beyond neon or other noble gases, we abbreviate the electron configuration of the previous noble gas by the symbol of the noble gas in brackets. So let's look at sodium. So sodium's electron configuration is 1s2, 2s2, 2p6, 3s1. Sodium has 1 more electron than neon. So this is neon's electron configuration. So you can just write neon in brackets. and then tack on the electrons beyond neon, which is just 3s1. So let's look at a couple more examples. Magnesium. Magnesium has 12 electrons. Here's its electron configuration. But as we just saw on the previous page, 1s2, 2s2, 2p6, that's neon's electron configuration. So we can write it as neon 3s2. For sulfur, it has 16 electrons. So again, here is neon's electron configuration. And then we just write neon in brackets and then everything after that. For gallium, 31 electrons. Here's its electron configuration. Well, it's past argon. So here's argon's electron configuration up to here. Argon is 1s2, 2s2, 2p6, 3s2, 3p6. So we got argon in brackets and then everything after that, 4s2, 3d10, 4p1. So this is really helpful so we don't have to write out, 31 electrons or 50 electrons. It's a nice way to abbreviate things. Okay, and then there are some exceptions to the filling order, and there's more than 5, but here are the 5 that you're responsible for knowing. And you can see here, in each one, either it has one s electron and then either a half or full d shell. So basically, the reason why this happens is that it's lower in energy to have half-filled orbitals or fully filled orbitals. So we would expect chromium to be argon 4s2 3d4 by its filling order. But it's actually 4s1 3d5 because it's lower in energy to have a half-filled s orbital and a half-filled d orbital. If we look at copper, same thing, same idea, right? We have a half-filled s orbital, but a fully filled d orbital. It's got 10 electrons. We would expect copper to be 4s2 3d9, but this is lower energy right here. And then palladium, I'm just going to point out, it doesn't have any 5s electrons. So we would expect palladium to be krypton 5s2 4d9, but it's lower in energy to not have any electrons in 5s and put them all in 4d. So these are the 5 exceptions. These are the ones you need to know. On the periodic table I put on D2L that I kind of pointed to you last week that shows you, everything above this red line, you need to know these element symbols and the element names. Well, it's got 5 atoms or 5 elements in blue boxes. These are the 5 elements in blue boxes. So I think that periodic table is a nice visual because it shows you what you need to know, right? What element symbols you need to know and names, and then the 5 exceptions. And you just need to learn these 5. There's more, but don't worry about them. Okay, let's talk about valence and core electrons. So valence electrons are the electrons in the outermost principal shell. So that means the principal shell with the highest N. They're important because they're held most loosely and they're the most easily lost or shared. So they're the electrons involved in chemical reactions. The core electrons are not in the outermost principal shell. They're not super interesting because they're not involved in chemical reactions or bonding. So let's look at this here. So we have silicon, 1s2, 2s2, 2p6, 3s2, 3p2. So its valence electrons are the electrons with the highest N. So the electrons in the N equals 3. So, and everything else is core. So N equals 1 and 2, core. Let's look at Se. So again, the valence are always the electrons with the highest principal quantum number. So its valence electrons are the 4s2 and the 4p4, even though we write the 3d10 after 4s2. So just the electrons in the n equals 4 orbitals are the valence electrons. So Se has 6 valence electrons, and then all the rest are core, and it's got 28 core electrons. So again, just the electrons with the highest principal quantum number. Here is some of the elements, common elements with their valence electrons written out. So what you can see here in a group is that, except for helium, as you go down the group, its valence electrons are all the same, except it has a higher N. So for group 1, their valence electrons are always S1. It's just N that's increasing. For hydrogen, 1s1, lithium, 2s1, sodium, 3s1. For group 2, its valence electrons are all s2 electrons. But again, see how N is increasing? So on and so forth. So the valence electron configuration is the same in the group, just increasing N. Okay, so from that we can divide the periodic table into 4 blocks, the S, P, D, and F blocks. So here's the S block, here's the P block, here's the D block, and here's the F block. So the main group elements are all within the S and the P block. These blocks divide up into what are the last filled electrons. So here our last filled electrons are S electrons, here they're P, here they're D, and here they're F. So how we can determine electron configuration from our periodic table is like this. Okay, so let's say we're looking at phosphorus, right? Well, its noble gas that comes before it is neon. So that's its inner electron configuration. Remember, we can just write neon in brackets. And then what we do is we go down here, okay, and we say we're in period 3. So through the S block, we're filling 3s2 electrons. Then we skip over, and now we're filling 3p electrons. And we count. We have 1, 2, 3. So what we are is NE, 3s2, 3p3. So in that group, you have your N is equal to your group or your period number. So 3, N is 3. And then we just count across. So we count across the S block, we have 1, 2 S electrons. And the P, we have 1, 2, 3. So that's what's really nice about dividing up into blocks. Let's look at another one. So for arsenic, the previous noble gas is argon, Ar. So that's our inner electron configuration. And then, okay, we go through the S block. So we're in period 4. So we have 4s, S1, S2. Then we go through the D block. The thing about the D block is that its principal quantum number is your period number minus 1. So when you're in the 4th period, your principal quantum number for D is 3, not 4, just to keep in mind. We go across here, we have D1, D2, D3, D4, D5, 6, 7, 8, 9, 10. So we're completely filled, which makes sense because we're going all the way across the D block. And then now we're in the P block, so we'll go P1, P2, P3. So the biggest thing to remember is that in the D block, its principal quantum number is the period number minus 1. So I was talking a little bit earlier about how the outer electron configuration for different groups is the same, just N is increasing. And that's why their reactivity is so similar. That's why they have such similar properties, right? It has to do with that. And this is why the alkali metals and the halogens are so reactive. Okay, so we want to get to a noble gas configuration. These are really unreactive because they have full shells. The 4s shell for krypton is completely full, and its 4p shell is completely full. So all the way down the noble gases, their s and p orbitals are completely full. So that means they're really unreactive. They don't really want to gain any electrons. They don't want to lose any. They're super stable. If you go to the alkali metals, they're each just 1 electron away from a noble gas configuration. Remember we saw earlier when we were doing the electron configuration for sodium? Its electron configuration was neon 3s1. So it's just got 1 more electron than neon does. So that's why it's so reactive. It wants to get rid of that electron so it can be more like a noble gas. This is also why the halogens are super reactive. They're just one less than a noble gas. So you can see here fluorine is 2s2, 2p5, and neon's 2s2, 2p6. Just has one more 2p electron. So the halogens, really like to gain an electron so they can get noble gas configuration. If we look at the alkaline earth metals, they're 2 electrons more than a noble gas. So they like to lose 2 electrons so they can be like a noble gas. This is why they're slightly less reactive though. It's a little bit harder to lose 2 electrons than it is to lose 1 electron. So the further away you get from a noble gas configuration, the less reactive that element will be. And this explains why alkali metals tend to form +1 ions. They like to lose 1 electron so they can be like a noble gas. So these form +1 electrons. These form +2 because they like to lose 2 electrons so they can become like a noble gas. Halogens like to become -1 because they like to gain 1 electron to become a noble gas. So again, like I just said, group 1A metals or group 1 metals like to form +1 electrons. We look at sodium. Sodium +1 has the same electron configuration as neon, a noble gas. It's happy. Again, group 2 likes to form +2 cations. Here's magnesium. If magnesium loses 2 electrons, it also has the same electron configuration as neon. Then group 17, they like to form -1 anions. Because if they gain an electron, see fluorine here is 1s2, 2s2, 2p5. If it gains an electron, becomes 1s2, 2s2, 2p6, it also now has the electron configuration of a noble gas. So this is another way we can predict ions that are formed. And again, it really only works for the ones I showed you earlier, group 1, 2, 7, and then those couple ones in the middle I showed you. But it makes sense now why they form those particular ions. They want to be like noble gases. If I can get to a noble gas configuration, I'm really happy. So again, here's the picture I showed you earlier of the ions that elements like to form. Okay, let's switch gears now and talk about periodic trends. So there's 3 main trends that I want you to know. And the first one is atomic size. So as you go down a column, atomic size increases. As you go across a period, it decreases. So down, increase, across, decrease. So I kind of like to generally think in up and over when I think about periodic trends. So if you go up and over, you're decreasing in size. Go up a column and over a period, I'm decreasing in size. To me, that's a little bit easier to remember because if I go down and over, my trends are not the same. Going down is increasing, over is decreasing. But if I go up and over, it's both decreasing. So just for me, that's how I like to think about it, but whatever works for you. And atomic size is determined by the distance of the valence electrons from the nucleus of the atom. So as I go across a period, the number of protons increases, which that means there's an increased attraction for the outermost electrons. So electrons are pulled closer to the nucleus, decreasing the size. As I go down a group, the size of the orbital increases with its increasing principal quantum number. So the electrons occupying the outermost orbitals are further from the nucleus. I don't really expect you too much to understand why these trends are the way they are. I just want to mention it. The biggest thing I want you to do is if I give you 2 elements, I want you to tell me what's bigger or what's smaller. One thing to keep in mind. Let's look at, for example, selenium and iodine. If I asked you which one's bigger, well, you can't tell just from periodic trends, right? Because if I go down one, I decrease, or I increase in size, but if I go over one, I decrease. See how they cancel each other out? So just from periodic trends, I can't determine what's bigger, selenium or iodine. So you have to keep that in mind. If I give you like sodium and aluminum, well, you should be able to tell me aluminum's smaller. But if I give you sodium and calcium, well, going down increases me and going to the right decreases me. So you can't just tell from periodic or from trends. So keep that in mind, that you cannot always tell what's going to be bigger or smaller based on trends. Okay, now let's look at ionization energy. So ionization energy decreases as I go down and increases as I go across. So again, I like to always think up and over. So if I go up, I increase. If I go over, I increase. Ionization energy is the energy required to remove one of the outermost electrons. So it makes sense that this has low ionization energy over here, because remember what I just said. The group 1 elements really like to lose an electron, so they have the noble gas configuration. So they have a low ionization energy. It doesn't take much energy to pull an electron off of sodium. The reason it decreases going down is because the atomic size is getting bigger, so that outer 1 electron is further from the nucleus, so it's even easier to pull it off. And then as I go over, it increases because it gets harder and harder to pull an electron off. So if we look here at the halogens for an extreme example, well, fluorine really does not want to lose an electron. Remember, it wants to gain an electron so it can become like neon. So its ionization energy is really high. Neon's even higher because if it loses an electron, it loses its noble gas configuration, which it likes. So that's why those trends are the way they are. And then if we look at, again, tin and bismuth, well, if I go, here's tin, here's bismuth, what has the higher ionization energy? Well, if I go down, it decreases, but if I go across, it increases. So again, this is another case of where I can't tell just from periodic trends. And then finally, metallic character. Metallic character increases as we go down, decreases as we go across. Again, I like to think up and over. So up decreases, over decreases. It mirrors ionization energy because metals tend to lose electrons and non-metals tend to gain electrons. So, the easier it is to pull an electron off, the more metallic it is. So that's really it that I want you to know for that. Again, I'm not too worried about you knowing why these trends are the way they are, but you should know what the trends are. So if I give you, again, 2 elements or a series of elements, you should be able to tell me, rate them from lowest to highest or highest to lowest. And you also should be able to tell me, hey, I don't know what's bigger or what's more metallic just from the trends, and here's why.